In this short video, let's take a look at the GARCH model for estimating volatilities. It's a pretty important concept as far as FRM exam part 1 is concerned. To understand what this model is all about, let's take a step back first and understand the difference between conditional versus unconditional volatility or variance. Let's assume that I have historically observed price series in front of me. Okay, I've laid them out in front of me. This price series, I can convert them into returns. I can square the returns and I can use those squared returns to estimate the variance. Okay. Now, if let's say I am standing at this point and I have the entire series in front of me. I know this series is already known to me. That's what I mean. And let's say I take all the observations in this series, put them in a container, mix them all up and use all these squared returns, for example, and compute a variance. As simple as that. That variance would not have taken into account the order in which these squared returns appeared. That variance is what I refer to as the unconditional variance. It's a variance which is not time varying, and I can assume this variance to be a long-term average and mean an average over all possible states that this data set captured. Okay. Now, let me try and do something differently. Let's do this. Let's start from this point, the point at which I was standing, but let's successively move forward in time. Let's say I move slightly forward in time, place myself at this time slice, and let's say I try and estimate the variance of my underlying asset with only taking into account the observations that have occurred till date. Okay, those observations I am assuming are recorded in this information set that I denote using a capital omega. Okay, so I am saying that if I place myself at time slice 1, then the estimate of variance which I arrive at is denoted by sigma 1 squared given or conditional upon the information till this time slice, and I call that information set as capital omega naught. Okay, let's say I move slightly further ahead. At this point, I re-estimate my variance. I call it sigma 2 squared because it's estimated as of time slice 2, given that or conditional upon the information which is available till this time. That information I'm saying is captured in the information set capital omega 1. Okay. If I keep doing that, then the situation which I am in on day n, for example, this was let's say day n. Okay. On this day, I'm assuming I'm standing on the morning of this day, estimating my variance, and I arrive at an estimate which I call sigma n squared, and this estimate has been arrived at using all recorded observations till this day n, and I call that information set as capital omega n minus 1. Okay. Why is it called n minus 1? The reason is that I am standing on the morning of day n. On that day, I still don't know what the closing price of my asset will be at the end of the day. The last closing price which I am aware of is the price which happened on yesterday. Yesterday is day n minus 1. Okay, and that's why I denote it as omega n minus 1. Now, if that is what I have done till now, that means I have been re-estimating my variance based on what is known to me till that day. The variance which I keep coming up with is what I refer to as a conditional variance. It's conditional upon the information available to me till that particular day. Okay. Now, this conditional variance, remember this, that it captures the time varying or the dynamic character of variance, the fact that variance changes over time. Okay. Now, what I'll be telling you now is two assumptions which I can, let's say, gather from this difference between conditional versus unconditional, and those two assumptions will come in handy when we, let's say, do a video on estimation of parameters of models that help you estimate conditional variance. We haven't yet looked at those models, but those models do have parameters which we estimate using, let's say, the maximum likelihood estimation, and those two assumptions which I'm about to state come in handy at that step. Okay. Now, if I am standing at this time point, okay, and if I were to ask you what is the distribution of the return that you will experience between, let's say, day n-1 to day n, that return, let's call it un. Okay, it's based on the closing price on day n-1 and the closing price on day n. If you're standing at this point and you are aware of this fact that variance / volatility has a time varying nature to it, a dynamic nature to it, then the distribution of this guy will not be normal. Okay, the distribution of this guy will have fat tails to it. If the variance has a time varying nature to it, you will arrive at a fat tailed distribution. But if I were to twist this question a bit and ask you, what is the distribution of un if I allow you to stand at this point in time? That means at the morning of day n. If that was my question, then you can say that the distribution which I am after is not really of un, but rather it's the conditional distribution of un given the information till day n, and that I captured using capital omega n-1. Okay. Now this distribution, which takes into account all recorded observations till the morning of day n, I can very well assume this distribution to be a normal distribution. All the time varying aspect of this volatility or variance of this distribution has already been captured in this information set. I know how I have reached this point of morning of day n when I started from day 0, for example. The path of stock prices between day 0 and day n is already revealed to me, okay? And therefore, this distribution, which is actually a conditional distribution, I can very well say, let that be normal, okay? Let that be a normal distribution with a mean 0, not a bad assumption to make, and with a variance sigma n squared. So this is my first assumption, and that is the distribution of returns, even in the case of time varying volatility, is conditionally normal. Assumption 1. If that assumption is true, and it's true that the mean of this return is 0, this will automatically imply that the expected value of the square of the returns that I will observe today in the evening when the closing price is revealed to me will be sigma n squared. Why is that so? Because sigma n squared, the conditional variance, I can write it as expected value of square return given the information minus the expected value of the return squared. Just the definition of variance, right? If the expected value of return given the information is 0, the second term will come out to be 0, and this expected value of square of the return is simply equal to the variance, okay? What was my second assumption? My second assumption, again, which I will need that in the MLE video, is the maximum likelihood estimation video, I should say, is that if I was standing at this point and if I were to ask you to pick any two returns that will appear in future and tell me if those returns are dependent or independent, then the answer is that they have a high chance of being dependent. There will be some kind of serial correlation between them, okay? If that were to be the case, how do we simplify things? We can actually simplify things if we don't look at the unconditional dependence versus dependence, but rather let's take a look at conditional dependence versus independence. That means take two returns, let's say un plus 2, try and check if they are dependent or independent, but taking into account the fact that you know all information till that date, okay? And if you were to do that, you will arrive at the assumption, which is a fair assumption to make, and that is returns are conditionally independent, okay? Again, something which will come in handy when we do maximum likelihood estimation. Now let's come to another question, and that is, if we are looking at a model which we are referring to as a GARCH model, Our first question is, wasn't the other model, which we've already taken a look at in a different video, the EWMA model, the exponentially weighted moving average model, wasn't that model good enough? Okay. Now, the EWMA model, it has two problems with it. The first problem is that if I were to write down the equation of the model, let's quickly recap it. It says that the updated variance as of the morning of day n is derived from two sources. It's derived from the recent most estimate of variance, the one which was done at yesterday's morning, that means morning of day n minus 1, and the most recent squared return. That means the return which was calculated from the closing prices observed yesterday and day before yesterday. That return is un minus 1. I square that return. In terms of the weights imparted to each one of them, the weight given to the sigma n minus 1 squared is lambda, the sole parameter of the EWMA model, and the weight given to squared recent most return is 1 minus lambda. Okay. Now, if I was standing on the morning of day n, and if I were to ask you what is your best guess of the variance of this underlying asset, that will happen tomorrow. Okay. The number which I am looking for is the expected value of sigma n plus 1 squared. Remember, tomorrow morning, given I am standing on day n in the morning. That means the information available to me is omega n minus 1. Okay. This is the number I am after. To get this number, all you have to do is take this formula for updating variance on a daily basis. Everywhere replace n with n plus 1. If you know the term which comes up, just take it as it is. If you don't know the term, just take it as its expected value. Just put n plus 1. What do we get? We get n plus 1 minus 1, which is sigma n squared. At the morning of day n, I already know that. So sigma n squared. Un plus 1 minus 1, that's un squared. On the morning of day n, I don't know that because this will require the closing price of the asset today in the evening. Okay. And therefore, what do? I replace it with its expected value. Here we said the expected value of un squared given I'm standing on sigma n minus 1 is sigma n squared. So that's what I put in here. Okay. What do I get? I get sigma n squared as my best guess of the variance tomorrow morning. Okay. If I were to repeat this actually for even 1 day ahead, that means the expected value of sigma n plus 2 squared, given I am still standing at the morning of day n, you can check this will also come to sigma n squared. So therefore, the EWMA model, what it's doing is it's giving me some kind of a flat profile as far as the expected variance is concerned going forward in time. It's a flat sigma n squared. That ways, the EWMA model is not able to capture something which we empirically observe, and that is mean reversion when it comes to variances. So variances, they do mean revert to some kind of a long run average kind of a variance. That variance we touched upon as this unconditional variance. Okay. So the EWMA model does not really capture that. Okay. So that's my first drawback. My second drawback of this model is in terms of its foundation, this model is resting on a single concept, and that is that we want, when we estimate our variances, to overweight recent observations. I mean overweight relative to older observations. Okay. This will be a better estimate of variances as compared to, let's say, taking all historical observations and giving them an equal weight. Okay. So this EWMA model, it's intended to actually capture that recency effect. I want my estimate of sigma n squared to be able to capture what is going on in the market at the current moment. Okay. And that's what the EWMA is based on. What this model does is that it imparts weights to historical observations in a magnitude which decays with time. That means the more further into history that you go into, the weight becomes smaller, and this rate of decay is exponential. That's the thought which EWMA is based on. Okay. Apart from that, the EWMA model is not based on any other econometric foundation. Okay. Now comes the GARCH model. Let's understand the equation of the model first. The equation of the model says that the updated variance as of the morning of day n is derived from three sources. It's a constant omega. This constant, as we will see very quickly, includes in it or houses within itself a long run variance, long run average level, that is VL. Okay. Plus you have some contribution coming in from the recent most squared return. The parameter or weight that we attach to this is alpha. Plus you have some contribution coming in from the recent most estimate of the variance, and the parameter which we attach to it is beta. Okay. In terms of what GARCH means, let's dissect each of these words in the acronym. The G means generalized. It's a generalized version of another model which is known as the ARCH. If I were to write down the ARCH model of order M, this model basically says that the updated variance sigma n squared is a constant, plus I will include M lagged terms of the squared returns. That means U n minus I squared. Okay. When I generalize this ARCH model, I do two things. First is I let this M potentially go to infinity. Second thing which I do is I also include in the model lagged terms of the variance itself. Let's call it beta I sigma n minus I squared. Okay. So not only the squared returns, I include in this updating procedure the lagged terms of the variance also, and the parameters are, let's say, beta I. That's what generalized means. Autoregressive, well, in this estimation procedure we are also including lagged terms of this variable which we are trying to estimate. We have included sigma n minus 1 squared, and that's why it's autoregressive. Conditional heteroscedasticity means that we are automatically trying to incorporate a time varying behavior in variance. Okay, and that's what the CH means. Now this is about the GARCH. This model has three parameters that we need to estimate: omega, alpha, and beta. And what we'll now do is that we will take a quick look at what each of these three intuitively mean. Now, take a look at this VL. We said that the omega houses within itself or includes within it a long run variance. We called it VL. Now, this VL is the unconditional / long-term average of the conditional. If I were to, let's say, peak really ahead in time, really ahead in time, then because of the mean reverting nature of variance, I would assume that the variance would have eventually come very close to its long run mean. That means in the GARCH formula, I'll be okay if I actually substitute for sigma n squared, I substitute VL. Sigma n minus 1 squared would also be very close to VL. That's what I do. And the squared return that I'll be experiencing really forward in time, peaking forward in time, my best guess of that will also be VL. If that is the case, I can, from this equation, back out what the VL is. That means if I know the omega, if I know the alpha, and if I know the beta, this formula would tell me what the VL is, the long run variance. Okay. Next comes alpha. What is alpha used for? It's a parameter or a weight which is assigned to the recent most squared return. In that sense, the same way as what the EWMA was doing, the alpha would tell you how much of the updated variance is coming from the recent most squared return. If the recent most squared return has, for example, spiked, the alpha will determine how much of this spike gets factored into my most recent variance estimate. In that sense, the alpha is a parameter or a weight which you can think as one which captures the recency effect or the reaction of variance to current shocks. Okay. What about beta? Connect this with EWMA. In EWMA, we had a single parameter lambda. So as the lambda decreases, as it becomes smaller, the decay rate becomes higher. The rate at which the weights decay over time becomes higher. The same kind of interpretation I can attach to the beta as well. Think of beta to be the decay equivalent in the GARCH world, the same role which lambda was playing in the EWMA world. Okay. Next comes alpha plus beta. Now, if you were to forecast your variance in the GARCH world, then you will see this term alpha plus beta appearing there. You will actually see the term alpha plus beta to the power k. Let's say I'm looking k days ahead. This alpha plus beta, think of it to be a term which determines the rate at which the conditional variance converges to the long run mean. Okay. If this alpha plus beta is high, the rate of convergence is actually low. If this alpha plus beta is low, the rate of convergence is pretty high. What we do is we define another variable, or another parameter I should say, let's call it gamma, which is defined as 1 minus alpha minus beta. So when alpha plus beta is high, it means gamma is low, which means the speed at which the conditional variance approaches the long run mean is actually small. When gamma is high, that means alpha plus beta is low. It means the speed of mean reversion is high. Okay. So this was a quick look at the GARCH model. We began with why we need such a model, and we ended up with both discussing what the model is all about and a look at an intuitive feel of what each of the parameters of GARCH basically contributes to the model.